Hi Carl, this is an example of the workspace in Hawkeye, and this would be an example here where we're looking at a survey location that's several thousand feet down in the well, and I have a little 3D cage there, and I have two other wells that are there. In the middle, what we have here is one of the ellipsoids which has been generated, and there's a number of tools that I have here for referencing where we are. One of them is these grid lines here, and I can turn those off. And the other one is this device right here, which is perpendicular to the direction that we're going, and I call this the sight, and we can look on this and we can see how far away we are by just without doing any measurements what there. These other two wells that are adjacent to the one that has the ellipsoid on it are I'm going to move down here, and then I'm just going to put it in a mode here where I can move down. We can see down here we have a target point where we hit where they all converge. And this isn't actually a terribly realistic scenario, but it's realistic enough for certain kinds of drilling applications. What we do here is we will calculate what the parameters are for this ellipsoid that we have, and I'll get a little bit closer in on it so we a little bit more clear. We will then calculate that for each one of the survey stations. Generally surveys are taken about every 30 to 100 feet, and then we generate covariant matrix out of that, error matrix, based upon the accuracy of how accurately we can measure the depth, how accurately we can measure the inclination, and how accurately we can measure the direction that we have. And then that's all the parameters and weighting functions that are used for those tools are incorporated in the determination of that covariant matrix, and it's from there where we get the dimensions. And then once we get those dimensions, depending on whether we're working with 1 sigma, 2 sigma, 2.5 sigma, 2.5 sigma in this instance will give us a 95% confidence level. So generally what's been done in the past is they not just what's always been done in the past. I'll go ahead and show you the other ellipsoid, which is often used. We will show that ellipsoid. And there's that green ellipsoid. Now the green ellipsoid is one that's calculated as a projection down to the north plane, and northeast plane of the actual one. The actual one has proven to be, I guess, too complex for people to calculate and to utilize. And in this case, you don't see a lot of difference, but this is a game about who has the most accurate numbers, blah, blah, blah. And sometimes, in fact, these two can diverge quite a bit, and in fact one of the big errors that these people make is taking the projection and mapping a projection on the 2D plane as opposed to actually figuring out what the cross-sectional ellipse is inside the actual 3D ellipse. But that's not, whatever logic is ultimately worked out would work on any ellipsoid, obviously, so I'm not really concerned about this. I'll go ahead and turn that other one off. And I'll turn on the intersection one. I turn on yet another. I have down below the screen here, I turn this one off and I turn that one on. And this new one is, well, you can barely even see it, but in this instance it's not clear, but it's where the lines get drawn when I choose these different modes. Now this mode right here is where we draw 3D lines all the way down the entire length of the well, and each one of those lines that we generate can be considered to be a plane essentially, and if it would make determination any easier of resolving this problem to be able to take those plane segments and calculate the minimum distance there. That would be you know, it'd be fairly straightforward for me to get those things into some sort of plane function. Now I'm going to turn on one more function here, and now we have everything is drawn. We've drawn the ellipsoids around just all the way down, and we have an ellipsoid in the middle. And then for greater clarity, I have one more visualization mode here where I don't draw the ellipsoid around my primary well, but I draw them around the rest. And now we're beginning to see how this, you know, the formation of the problem here, and is calculating the closest point from here to this well. Center to center is pretty straightforward, and that's a segment to segment problem. And if you look very carefully here, you can see a red line that goes across here. It's a little bit more clear if I turn this sight off, and you can see that, and that it's pretty obvious that in a case like this, it would almost be certainty that the nearest point on this ellipsoid to this elliptical cylinder would be somewhere along that line right there, or very close to it. And so that's always a good way of choosing you know, an iteration point if I wanted to solve this numerically. But in this case, you can see there's another well here, and you can see how this straight line distance right here, the shortest distance being calculated to this other well as we move down, is not on that plane, and it's not on something which is intuitively obvious as being the point which is closest. There may or may not be. The closest point in this case, since this closest distance here is actually emanating somewhere from the bottom of this ellipsoid, the closest point may be somewhere on the outer fringes of this, more directly associated with a point over here or something. And then there's just myriad kinds of examples that can be shown of wells that are passing above or below, or depending on the orientation of this ellipsoid, and how it, you know, different scenarios that you can have. And then that is used, that distance, which is the distance in between the outer cylinder and the ellipsoid, is referred to as the separation factor. And the separation factor is used in risk analysis when the directional, or when the drilling companies, or oil companies in particular, since they're the ones that employ the people to study this stuff, are determining whether or not they should drill in a particular area or not, how far away they are. And their whole goal is to try and optimize the amount of wells that they can drill in a given field, and at the same time minimize the total amount of risk that they are exposed to. So anyway, I hope that makes it a little bit clearer, and I hope that this isn't too long-winded. Again, I really do appreciate you thinking about this for me and letting me know if I should pursue a numerical route or not. But anyway, it's neat. It's a kind of curious problem. I think it's a neat problem anyway, so I think you do too, so that's great. But I'll talk to you later. Bye.